Today we've got a nice problem that was inspired by something that I found in a 2014 issue of Mathematics magazine. So let's say we're given a recursively defined sequence, and it's defined by the following one-step recursion. an plus 1 is equal to half an squared plus 1. And then our goal is to determine all values of, well, the first term of this sequence, so that the sum as n goes from 1 to infinity of 1 over an plus 1 converges. And we're going to put a restriction on a1 so that it's a positive real number. You'll see that if you take a negative real number, well, then you can see that a2 will be a positive real number. So that really just shifts the argument a little bit. And then if you take a1 to be 0, you'll see that a2 again is a positive real number. So again, that just shifts the argument a little bit. Okay, so we're going to start off by recalling something called the test for divergence. And that has to do with if a series converges, then what do we know about the limit of its terms? Okay, so let's recall that here. So if the sum as n goes from 1 to infinity of 1 over an plus 1 converges, then that means that the limit as n goes to infinity of 1 over an plus 1 must equal 0. So notice this is called the test for divergence. It is not a convergence test. And that's because this is a condition on convergent sequences, but it's not an equivalent statement for convergent sequences. Because this is a condition on convergent series, but it's not an equivalent condition for convergent series. So you could potentially have a series that diverges, but its terms also tend to 0, like for instance, the harmonic series. So this is really just going to give us a gut check for, is there a possibility of convergence or not? Okay, so let's maybe spell that out over here. So we need this from, again, this test for divergence, the limit as n goes to infinity of 1 over an plus 1 to be equal to 0. But if that limit equals 0, then the limit of the reciprocal must be positive or negative infinity. So let's write that down. So we have the limit as n goes to infinity of an plus 1 must be equal to, well, like I said, plus minus infinity. But I'm going to argue here that positive infinity is the only possibility. And that's because notice that all of these are positive numbers. That's because, well, we're taking our seed to be a positive number, but then we've got the square of a real number, which is always positive, plus 1. Okay, so if you've got only positive numbers here, and we know the limit is plus or minus infinity, then of course the limit has to be plus infinity. Okay, so anyway, so that tells us that the limit as n goes to infinity of a sub n must be infinity. Okay, so that's a necessary condition. It's not a sufficient condition, but it is a necessary condition for our series over here to converge. Okay, now moving forward, we're going to break this into a couple of cases. So this thing that I'll maybe call case 1 will be the case when a1 equals 1. But notice if a1 is equal to 1, by our recursion right here, that tells us that a2 is equal to a half times 1 squared plus 1, which itself is equal to 1. But then we can apply the recursion again and see that that means that a3 is equal to 1. And in fact, that means that an equals 1 for all n. But that means a couple of different things. That means that the limit as n goes to infinity of a sub n, well, that's going to be equal to 1, which is not equal to infinity, which by our observation up here, that means that our series diverges. But then also we could just immediately see that our series in this case is the sum as n goes from 1 to infinity of 1/2, which we can also see kind of obviously diverges because we're just adding a half to itself infinitely many times. Okay, so now let's move on to our second case. So our second case will be the case when a1 is less than 1. So here we have 0 is less than a1, which is less than 1. But now what I'll do is I'll write a1 as 1 minus b, where b is some number between 0 and 1. So we want to see like how far away it is from the number 1. And now, in fact, what we're going to do is show that in this case, the sequence also has a limit which is not infinite. And since the sequence has a limit which is not infinite, well, we know that we have divergence. But how can we do that? Well, the classic way to do that with recursively defined sequences is the monotone sequence theorem. So let's use the monotone sequence theorem. So let's first show that our sequence is monotone. And in fact, what we'll do is show that it's increasing. And how do we know to show that it's increasing and not show that it's decreasing? Well, I think maybe you could do some numerical tests here. You could maybe start with a1 equal to 1/2 and run through the situation. So notice if a1 is equal to 1/2, then a2 is equal to, well, let's check it out. It'll be 1/2 times 1/2 squared, which is 1/4 plus 1, but 1/4 plus 1 is 5/4. Divide that by 2, you get 5/8. But notice that 5/8 is bigger than 1/2. And then you can check that a3 will be itself bigger than 5/8 and so on and so forth. So it looks like it's increasing. So anyway, let's show that for our more general setup. So let's do this by induction, and we'll do a base case to show that a1 is less than a2. Okay, so let's write a2 here is going to be equal to 1/2 a1 squared plus 1, but I can write that as 1/2 and then 1 minus b squared plus 1, given the fact that we've written a1 in that form. But let's see, that's going to be 1/2, and then multiplying this out, what will we have? So we'll have, let's see, b squared minus 2b plus 2. That's what we get like after all is said and done. But now we can take this half and distribute it through and then rewrite this a little bit as 1 minus b plus b squared. But let's see, 1 minus b is a1, and then we're adding b squared on. But b squared itself is positive. So that means we do have something which is bigger than a1. So we have shown that it's increasing. Okay, so now that we've shown that it's increasing, let's show that it's bounded above. Okay, so now let's show it's increasing, and we'll do this by induction. So our base case will be to show that a2 is bigger than a1, and this is a pretty quick calculation. So let's write a2 as 1/2 times a1 squared plus 1. Notice that's just using our recursion here. But now we can plug 1 minus b in for a1. That leaves us with 1/2, and then we'll have 1 minus b quantity squared plus 1. Multiplying that out, we get something pretty interesting. We'll have 1/2 2 minus 2b plus b squared. So I expanded that and combined like terms. But now distributing the half through, you'll see that we get what? It'll be 1 minus b plus 1/2 b squared. But 1 minus b is equal to a1, and since b is between 0 and 1, half b squared is positive, meaning this whole thing is bigger than a1. So let's see, we've got in the end, a2 is bigger than a1. So that sets up the base case for our induction. So now let's make an induction hypothesis. So let's suppose for some k bigger than or equal to 1, we know a k plus 1 is bigger than a k. But now essentially what we just do is the operations on both sides that will build the next term via the recursion. So if AK plus 1 is bigger than AK, then that means that AK plus 1 quantity squared is bigger than AK squared. But then we can add 1 and divide by 2, and you'll see that we immediately get AK plus 2 is bigger than AK plus 1. So that finishes the inductive argument that we indeed have an increasing sequence. Okay, so now let's show that it's bound above. So in the case when A1 is between 0 and 1, we've just shown that that means our sequence is increasing. Now we'll show that it's bound above, and we'll show that it's bound above by 1. So notice that our base case is just built into our assumption. A1 is most definitely less than 1. So that means we just need the induction step. So let's suppose for some k bigger than or equal to 1, we know AK itself is less than 1. But now let's do the operations just like we did before. So let's square both sides. So that'll give us AK squared is less than 1 squared. But then in turn, that'll tell us that 1/2 AK squared plus 1 is less than 1/2 1 squared plus 1. But notice this part is AK plus 1, and then this part is simply 1/2 1 plus 1, or in other words, the number 1. So it follows that if AK is less than 1, then AK plus 1 is less than 1. So that means that it's bound above. Okay, so our sequence is increasing and it's bound above, but that means it converges. Well, in fact, it means that the limit cannot be infinity because all of the terms are bound above by 1. That being said, we could calculate the limit of this sequence just to like maybe cross all of the T's and dot all of the I's for this situation right here. Okay, so let's do that over here just for fun. So let's set the limit as n goes to infinity of a sub n equal to a. But taking the limit of these two sides will give us a nice equation. A equals 1/2 times a squared plus 1. But we can rewrite that as a squared minus 2a plus 1 equals 0. In other words, a minus 1 quantity squared equals 0, which tells us that a is equal to 1. But that tells us that the limit of our sequence is equal to 1, but that's not infinity, kind of obviously. But that means that we have to have divergence here because an infinite limit here was necessary condition for convergence. So that means we've got divergence in case 1 and case 2. Now let's look at the last case when A1 is bigger than 1. So we just showed that if A1 was between 0 and 1, not including 0 but including 1, and actually you could maybe do it as a little bit of a homework exercise, that this also works in the case when A is equal to 0. But anyway, in all of those cases, the limit of our sequence was equal to 1, which implied that our series that we're interested in diverges. That's because a necessary condition for convergence is the limit of the sequence must be infinite. Now we're going to look at our last case when A1 is bigger than 1. And notice this will also kind of be the case when A1 is less than -1 because that means that A2 itself is bigger than 1 and you can just shift everything. That's why looking in this region right here is kind of enough. Okay, so anyway, what we'll start off with is showing that this thing is increasing. Okay, so let's do that. So how might we do that? Well, we're going to do it by induction again. But before we start our inductive proof, let's rewrite A1 as 1 plus b, where b is a positive number. You can do that for any number bigger than 1. Okay, so now let's show that A2 is bigger than A1. So here A2 will be equal to half A1 squared plus 1, but that'll be 1/2. And then 1 plus b quantity squared plus 1. But now we can multiply that out to get 1/2, and then we'll have 2 plus 2b plus b squared. Again, just by some simple symbolic manipulation. But then that'll pretty clearly give us 1 plus b plus 1/2 b squared. But then again, 1 plus b is A1, pretty similar to our other case. It's not 1 minus b this time, but this is pretty clearly bigger than A1. So again, we have an increasing sequence because A2 is bigger than A1. I shouldn't say we have an increasing sequence yet. We've proven our base case to show that this is an increasing sequence. But now our induction step will be the same. So I'll just maybe put that here. So same induction step. Because notice the induction step didn't really depend on the starting term. It just was doing symbolic manipulation on an arbitrary inequality. Okay, so same induction step. So we know that this is increasing. Okay, so next up, I'm going to show that this is in fact unbounded. And how can we show that this is unbounded? Well, we're going to do it by way of contradiction. So by way of contradiction, suppose that there exists some number m such that a sub n is less than m for all natural numbers n. But then that's where we're going to run into a problem, because then we'll have a bounded sequence that is increasing. But if we've got a bounded sequence that is increasing, it converges. But that means that it must converge to 1. So we have the limit as n goes to infinity of a sub n equals 1. And that's because that's the only place it can converge by our previous calculation. But now, since this thing is strictly increasing, this limit is going to be most definitely strictly bigger than the starting term. But then the starting term is bigger than 1 by our assumption. Oh, but look, we've got a major problem here, because now we've shown that 1 is strictly less than 1. So there's our contradiction. So that means that yes, this thing is unbounded. But this thing being unbounded is exactly what we need for the limit as n goes to infinity of a sub n to be infinity. So that means that if a1 is bigger than 1, we have the necessary condition for convergence. Now we just have to show that we indeed do have convergence. So now we're ready to finish this thing off. Let's recall that so far we've proven that the possibility of convergence only exists if a1, the seed, is bigger than 1, strictly bigger than 1. And in that case, the limit of the sequence an was equal to infinity. And now we'll show that we in fact do get convergence in all of those cases. Okay, so how can we do that? Well, there's a nice calculation that'll finish this thing off. So let's start with 1 over an plus 1 minus 1, and observe by our recursion, we can write that as 1 over 1/2 times an squared plus 1 minus 1. But then, doing a little symbolic manipulation on this, this turns into 2 over an squared minus 1. Oh, but look, this is perfectly set up to do partial fraction decomposition. And I won't go through the steps of that because that's fairly elementary. But what you end up with is 1 over an minus 1 minus 1 over an plus 1. Oh, but look, this 1 over an plus 1 is exactly the term inside of our sum. So let's solve for that. So that means that 1 over an plus 1 is equal to 1 over an minus 1 minus 1 over an plus 1 minus 1. And that really motivates us to think that some sort of telescoping action will happen in our final calculation. And it will, and let's see that. So now our goal sum, so the sum as n goes from 1 to infinity of, let's see, 1 over an plus 1, via this and writing it as a limit of partial sums can be rewritten as the limit as capital N goes to infinity of the sum as n goes from 1 to capital N of 1 over a sub n minus 1 minus the sum as little n goes from 1 to capital N of, well, kind of the same thing, but now it's 1 over a sub n plus 1 minus 1. But check it out, both of these sums have almost everything in common. It's just that the first sum has an n equals 1 term, which is different from anything in the second sum, and the second sum has a n equals capital N term, which is different from everything in the first sum. So that means after taking all of the differences, that's all that remains. So that leaves us with the limit as capital N goes to infinity of 1 over a1 minus 1. So that's the remaining term from the first sum minus 1 over a sub capital N plus 1 minus 1. That's all that remains in the second sum. But let's recall that in this setup, we know that the a sub n terms go to infinity, but that means this denominator also goes to infinity. That means that whole object, which is maybe the remainder part, goes to 0, meaning we're left with just this first term, which is 1 over a1 minus 1. And that's the final value of this sum. And let's recall that a series converges if and only if its sequence of partial sums converges. And we've shown that as long as a1 is bigger than 1, the sequence of partial sums converges, and thus our series converges. And that finishes this whole thing off. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.